Good evening, students. I'm just going to give you a brief introduction of what I would like you to do for your GCSE physics work this week. If you remember the last lesson that we covered, we introduced the idea of the evolution of stars. And we talked about how stars are formed and about how stars produce their energy, stars like the sun. We didn't get as far as talking about the end state of a star's life, so the death of a star. And so that's what we're going to finish this week. There is a homework sheet. Now, what I've done with the homework, because obviously with me teaching you remotely, it's going to be difficult to sort of collect them in and mark them and so on. With the homework, I've attached it to show my homework in two different formats. I've attached it as a Word document and also a PDF document. Now, if you're able to edit a Word document, this is how I would like you to do the homework on the Word document. So what I would like you to do is open up the Word version of the homework, add the answers in electronically. There's spaces, there's boxes and spaces for you to add in the answers to the homework electronically, and then save it, and then reattach the homework completed to Show My Homework. I can select on Show My Homework student submission rather than class submission, which means that you can reattach the homework to Show My Homework once you've completed it. So you can attach the Word document. If you can't access a Word document, I know some of you only have Apple machines and so on at home that can't open Word documents. If you can't open a Word document, then what you'll have to do is open the PDF version of the file, print it out, and then obviously do the homework by hand, either on the sheet or on a separate piece of paper. What you'll have to do then is photograph or scan your completed homework, and then attach that scan, probably be a JPEG file, back to Show My Homework. But it's a lot easier for me, and it's a lot easier for you if you're able to just do the Microsoft Word version, and that doesn't involve any printing out. You can just edit it electronically, and then save it, and then reattach it to Show My Homework. And that's how we'll try and do the homeworks in the weeks ahead. To be honest, we've only got a little bit of the course left. Because we've almost finished about halfway through space physics. After that, it's really just going to be revision for you guys. And I know you may not have an exam coming up, but we still have to treat the end of the course as if you do have the exam coming up, and therefore you do still have to revise. We don't know exactly how the assessment is going to work. We're still waiting for details of that. Okay, so the death of stars. What would be really helpful is if you have the CGP textbook. If you do have the CGP textbook, then you can read, I've got one here, you can read page 318 and 319, which covers the whole of evolution of stars. There's also some practice questions at the end there. So that would be one thing you can do, and maybe make some summary notes in your exercise book. Another thing you can do as well is, and I'm going to attach to Show My Homework, is a diagram showing the complete life cycle of stars. So if you could print that out and stick it into your exercise book too. There's also the homework, of course, that I've just mentioned that you're going to have to do. The deadline for that is going to be Tuesday. So if you can get that homework done for Tuesday, and then I'll set some more for the end of the week. The other thing that I would like you to do is I would like you to watch a video, which I'm going to post the link to that on Show My Homework. Just to very briefly go over the end part of the evolution of stars. We left it at the end of the last lesson talking about a normal star like the sun is fusing hydrogen into helium and releasing a huge amount of energy as it does so. And this keeps the star in balance because you have gravity pulling the star inwards, and you have radiation pressure from this nuclear reaction that's pushing the star outwards. And this balance will continue for billions of years. In the case of the sun, probably about 5 or 6 billion years into the future. Eventually, and this happens to all stars, the amount of hydrogen in the core will deplete. And of course, you need hydrogen to fuse into helium. And when the amount of hydrogen in the core starts to run down, what happens to the star is that it will start choking on the if you like, the dregs of its fuel. You need to fuse hydrogen into helium to produce energy. If that can't happen, the core of the star will start collapsing because of gravity, and it will collapse and get hotter. And as it gets hotter, helium itself will start fusing with other helium nuclei and forming heavier nuclei such as carbon and nitrogen. It's a different fusion reaction to the one that's going on in a main sequence star like the sun. And when this helium reaction turns on, it releases much more energy than the hydrogen reaction. And that will push the outside envelope of the star outwards. So the star actually, it becomes much more luminous, but it also expands to a huge diameter. In the case of the sun, it will expand to about the size of the Earth's orbit. So the sun will fill the entire orbit of the Earth. Mercury and Venus will obviously be enveloped by the sun and will be destroyed. The Earth may well be destroyed. The Earth will certainly be too hot for any life within perhaps 1 billion or 2 billion years from now. If the Earth does survive, it will be because it will move slightly further outwards and just escape being swallowed up by the sun. But it will still be far too hot for life to exist. As it is billions of years into the future, it is somebody else's problem. But that's how the sun is going to end up as what's called a red giant. Now, what happens next after the red giant phase does depend on the mass of the star. The sun is what we call a low mass star. And what would happen to the sun is that the helium fusion would eventually switch off, just like the hydrogen fusion switched off before. And when that happens, the star essentially dies. There's no more fusion going on. The outer layers of the star would just drift off serenely into space and form what's called a sort of planetary nebula, which is sort of a disc-shaped nebula surrounding the sun. The center of the sun, the core of the sun, where the fusion reactions were happening, that would survive as a kind of a stellar corpse called a white dwarf. The white dwarf is a very hot, very dense object. It's about the size of the Earth, and if the Earth did survive the red giant phase of the sun, it would carry on orbiting this tiny little white hot ember, this white dwarf. The white dwarf is just glowing by its residual heat and will carry on glowing probably for trillions of years until it eventually goes black. And some people have called the end state a black dwarf, but there aren't any black dwarfs in existence yet because the universe isn't that old enough yet. So this is what would happen to the sun in billions of years' time. Red giant, and then the outer layers blow off into space, not as an explosion, just gently drift off, and then the core collapses as a white dwarf. That's a star similar to the sun. If you've got a star which is at least 5 or more times massive than the sun, it will have a much more dramatic death. And that's because the helium fusion doesn't switch off at the red giant phase. Well, it does switch off eventually, but when it does switch off, the core of the star carries on contracting and getting hotter until other fusion reactions switch on as well. And in fact, the core of the star will carry on fusing elements beyond carbon, beyond nitrogen, all the way up towards iron, which is element number 26 in the periodic table. It will fuse elements up to iron. When it gets to iron, it can't fuse any more elements. Iron is the heaviest element that you can fuse and get energy out. At this point, the star, which will be absolutely enormous, it's sometimes called the red supergiant. It'd be about the size of Jupiter's orbit if you put it in the solar system. At this point, the star becomes violently unstable. It can no longer support the gravitational pull of all the outer layers pushing downwards on the core, as the core is no longer producing energy. And the entire star collapses and then rebounds in a massive explosion called a supernova. And that's it for the star. As it blows up as a supernova, it will release as much energy as a normal star does in its entire lifetime within the space of a few days or a few weeks. In fact, a supernova can glow with as much light and as much energy as an entire galaxy of stars for a short period of time, like billions of stars. So a supernova, a very dramatic death of a star. What happens next after a supernova is quite interesting. It's not quite the end. First of all, the outer layers of the star that are blown off into space, they will contain very heavy elements. Not just the elements up to iron that the star formed during its lifetime, but also elements heavier than iron that were formed by fusion during the collapse of the star. These elements are crucial for life. They're crucial for building planets and also for biological life. You couldn't exist without elements like zinc and phosphorus and so on inside your body in small amounts. So actually, these deaths of huge stars form an important part of the creation of life in the universe, because these elements get scattered all the way across the universe in these colossal explosions. The center of the star that blew up as a supernova, the core of the star, can also survive as a very, very exotic object. Much more exotic than the white dwarfs that form from normal stars when they die. The core will be incredibly dense, and gravity will keep on contracting it way past the stage of a white dwarf, and you'll end up with one of either two extremely dense and extremely exotic objects. The first exotic object you might end up with is a neutron star. And a neutron star has most of the mass of the original core of the star, but concentrated in a tiny sphere, perhaps the size of Manchester or Birmingham, about 20 kilometres across. Incredibly dense. If you take a piece of neutron star, which is the size of a grain of sand or a grain of salt, it'll weigh as much as 10 aircraft carriers. It's that dense. And the neutron star also spins very rapidly. Some of them can spin hundreds of times a second, so faster than your washing machine on its spin cycle at home. So they can spin incredibly quickly. They can give out beams of radiation, which sort of fly around the universe. They're sometimes called pulsars when that happens. And that can be the end state of a supernova explosion. So the core can collapse and form a neutron star, as the name suggests, made out of neutrons, very closely packed together, similar to the protons and neutrons in the nucleus of an atom. The other possible end state is perhaps even more exotic than a neutron star, and you've all heard of these objects. They're called black holes. And the core of the star doesn't stop collapsing at the stage of a neutron star. It carries on collapsing, and it becomes so dense, and the mass is so concentrated, its gravity is so strong that not even light can escape from it. A black hole is I suppose the ultimate end point of a star. No light can escape, no matter can escape from a black hole. The entire mass of the core of the star, as it once existed, is concentrated within a very, very, very small volume. And so that's a black hole. You may wonder how we know black holes even exist, as they can't emit any light. Well, you can't emit light from inside the black hole, but material that falls into a black hole can get heated up and can give out X-rays before it finally disappears over the edge of the black hole, what's called the event horizon, and vanishes from the universe forever. So those are the endpoints of a star. A star will expand into a red giant or a red supergiant. If it's a low mass star like the Sun, it will end up as a white dwarf, the core of the star. If it's a high mass star, then the red supergiant will explode as a supernova, and you may be left over with the core of the star becoming a neutron star or a black hole. Okay, that's it. Don't forget to do the homework by Tuesday, please. And on Tuesday, we'll give you the next load of homework. Okay, thank you. Have a good night.